Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. One of the most common causes of endogeneity is reverse causality. And the problem is quite simple. We think that X causes Y. However, we don't know whether Y causes X, and there will be cases where indeed Y as well will cause X. But if that happens, what about our regression? Our regression is no longer telling us what we think it is. Reverse causality, also sometimes called as simultaneity, is the case where both variables are determined simultaneously, making it impossible to cleanly separate cause and effect. Let's write this down. So reverse causality, also simultaneity, because while X is causing Y, also Y is causing X. Suppose that you are estimating the usual model Y equals to beta 0 plus beta 1X plus an error term. When we run this regression, we're assuming that the direction is going from X to Y. Examples? We've seen many in the previous videos, but let's take a few that will make the point for this entire simultaneity and reverse causality thing. We'll take education and income. We'll take exercise and health. And we'll also take police and crime. Okay? In each case, we're telling a story where X moves first and then Y responds. That's the implicit assumption that we've basically baked into every OLS regression. So higher education, higher income. The more you exercise, the healthier you are. The more police, the less crime you have. Now, the hidden assumption, keep in mind here, we're always looking at this direction, X to Y, all right? It has a direction. It says X changing, Y responding. X the cause, Y the effect. But in the real world, many relationships don't work this neatly because variables often influence each other simultaneously. And in an experiment, we could force X to change and observe Y. In observational data, obviously we can't do that. And the reverse causality is basically one reason why. So what does reverse causality really mean? In this case, what I am assuming is that there is an arrow that actually goes in this direction. So when we observe that X and Y move together, the question now becomes, how much of that is it caused by X causing Y, and how much is Y actually causing X? And the thing is, OLS, unfortunately, cannot separate these two stories from one another. It just sees the correlation, and what it will do is attribute all of it to X. For instance, with education and income, we often think education is the one that is causing income. More education will lead to higher earnings, which obviously makes sense. But think also at the same time, expected future income could also affect how much education someone gets, right? Because people who expect higher returns will invest more in education. While you are in your job, you might think, well, now it's about time I get a specialization or I get a master. And you can, because the higher income that you have will allow you to get into that further education. So that means that this arrow now no longer exists only from education to income, but also in the direction from income to education, right? And this is also one of the reasons why return to education is one of the most studied and most debated questions in labor economics. Separating the causal effect from the reverse causality is genuinely difficult. But one of the examples that is mostly discussed, and one of the examples that with a very high probability you will see in the slides in your lectures, is the one of the relationship between police and crime. It's actually a relationship that has been noted in econometrics since the 1940s to 60s, when econometrics was being researched, until in 1997, Stephen Levitt actually published a paper using electoral cycles in police hiring to estimate the effect of police on crime. And the results of that paper and that paper itself get cited a lot of time, and it's the actual example that most of you will see in your lecture slides, because it's one of the most classical IV applications. Some of you might also see the paper, the example on the paper of the 1992 on Los Angeles riots to identify, again, the causal effect of police on crime. But as I said, the most typical one is the one with electoral cycles in police hiring. In here, the example is very clear. You've got police and crime, which the naive conclusion would be that police is causing crime, because the more police you have deployed, the crime should deter. However, there is also the other side of it. You are deploying more police because the crime rate is higher. So the causality runs both ways. More crime causes more police, and the other way, okay? So if we regress crime on police, we pick up both effects simultaneously, and the OLS estimate is basically a mess of both causal direction. Now, why does OLS struggle? Remember, one of the assumptions that we've been carrying through this entire econometric series is the fact that the covariance between x and u, the error term, is actually 0. But when y affects x, it means that something in here in the error term that is part of the y is actually affecting x, right? Which means that in the case of the simultaneity issue, this assumption will actually no longer be true, okay? Because the feedback from y to x is contaminating x, and the OLS is picking up this contamination and attributing it to your beta 1, meaning that the estimate is not only biased, but also inconsistent, okay? Now, keep in mind, this is structurally identical in a sense to what we have seen with omitted variable bias, but just a different channel. Because in omitted variable bias, you had y and x, and of course you had the error term, and you said that there is an x2 in here that actually affects the y, while x1 is affecting y, okay? In the case of the simultaneity, what we're saying is that it's not the x2 that is in there, but like some part of this u that is affecting. So this goes basically both sides, and this would go both sides as well. Now, the big consequence is that the regression coefficient still measures association. High x, for instance, tends to go with high y, that's real, but it no longer measures causal effect. So it's a mixture of the effect of x on y and the effect of y on x. And this distinction is very important, especially for policy, because let's put it into context for the police crime example. If you think police reduce crime, but actually crime is the one that's driving police deployment, it means that sending more police to reduce crime might actually not work. Reverse causality, once again, occurs when x affects y and y also affects x, creating endogeneity that prevents the OLS from recovering the clean causal effect. So as we said, we'll have biased and inconsistent estimates. In the next video, we'll visualize reverse causality using a path diagram and see exactly how the feedback loop creates this violation of the assumptions that covariance of X and U is equal to 0. So stay tuned, and I'll see you in the next video.